Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for July 25th, 2012.
On this week's show, a new headlight system prototype shines between, not through, rain and snow. Loops of light optically detect single molecules, and 2 new lasers come to light.
Anyone who's ever driven a car at night in the snow or the rain, and that's pretty much all of us, knows what a blinding experience that can be. Well, researchers at Carnegie Mellon have devised a system that would eliminate raindrops and snowflakes from your field of view. I spoke with project scientist Robert Tamburo about how it works.
The way the system works is the camera actually captures an image, and then it looks for raindrops in the image. And if it finds a raindrop, then the computer, using our algorithms, detects the raindrops and then predicts where they're going to be in the future. And then based on where they are in the future, we control the light projector to not illuminate that area. So there's 3 main components to our system. There's the camera, there's the projector, which we use as our light source, and there's a computer. So there's a 13 millisecond lag between processing steps. The main reason for that is that the components that we use, they're all off-the-shelf components that are just kind of hooked up through Ethernet cables and VGA cables. So a lot of our latency is due to transferring data between these components. So what we're working on is trying to integrate all of those components more closely together. So that's the idea for current research in making this thing faster.
It also would automatically dim for oncoming vehicles and that kind of thing?
Yeah, so you can use the camera to find things in the image and then control the light based on what you found. So in our project, we've decided that, we want to find raindrops in the image and control the light to avoid illuminating the raindrops. But you can do things like there's an oncoming car headed your way. You can find the driver's head in the image and then control the light to turn off so that it doesn't blind the driver. You could also, instead of controlling the light to turn off, you can make it brighter, for example. So if there's, an obstructed stop sign, maybe you can, analyze the image, find the stop sign, and then, maybe for those light rays that would hit the stop sign, you intensify them more so that the stop sign is more visible to the driver. Once you have the hardware in place, you can write different algorithms to do different types of detection. So instead of detecting raindrops, you can detect deer on the side of the road. You can even detect things like, pedestrians in the crosswalk, make drivers aware of the pedestrians. For controlling light, it's basically a projector, and people watch movies on projectors. So you kind of project things that aren't on the road onto the road. So one of the problems driving at night when it's raining is you can't really see the lane markings in the road anymore because of all the glare. If you had the algorithms that were sophisticated enough, you can project the lines onto the road so that the driver could see them when they otherwise couldn't.
Tamburo estimates it will take 3 to 4 years to take the system from 120 Hz currently to the 500 Hz needed to deal with real-world effects like wind, vibration, and rapid movement. Their goal is to achieve 70 to 80% accuracy, which would significantly improve the driver's visibility and reduce their stress. We have an additional demonstration and presentation by lead researcher Srinivasa Narasimhan, which is linked here, and you'll also find it at the end of this show.
Optically detecting single molecules currently involves using metal nanostructures to focus light into tiny hotspots, which excite surface electrons. When shone on a molecule, these oscillating electrons help the focused light increase a molecule's signal enough to be detectable by optical microscopes. This method is limited because the hotspots are very small and can get too hot, melting the nanostructure and destroying its ability to channel light effectively. A new nanoscale light manipulation method developed by an international team optically detects single molecules and could be used in a variety of photochemistry applications. They increase the useful area by shining circularly polarized light on gold nanostructures. This light imparts a sense of rotation on the electron density in ring-shaped gold nanostructures, trapping the light in the rings and forming loops of light. These light loops cause excited electrons to oscillate coherently on the full surface of the square-ringed nanostructures, rather than in a few concentrated hotspots. This increases the opportunity for interaction with molecules. The study appeared online in Advanced Materials.
LED pioneer Shuji Nakamura and his group at UC Santa Barbara developed the first violet nonpolar vertical cavity surface-emitting lasers based on M-plane gallium nitride semiconductors. Nakamura said they believe it to be one of the biggest breakthroughs in laser diode technology. The electrically injected VCSEL platform lasers at room temperature and provides high optical gain, which helps to increase optical efficiency of lighting, displays, and sensors.
Electrical engineers in Texas and Wisconsin have devised a new laser for on-chip optical connections that could give computers a huge boost in speed and energy efficiency. Surface-emitting lasers necessary for such high-speed optical links between computer cores could be 20 to 30 microns tall, dwarfing their silicon surroundings on a 1.5 micron optically connected chip. The researchers propose replacing layers and layers of reflectors necessary in the traditional distributed Bragg reflector laser design with two highly reflective photonic crystal mirrors. One layer of photonic crystal is equal to about 15 to 30 layers of dielectric reflectors found in conventional lasers. The resulting surface-emitting laser's profile is vastly lower, 2 microns in height, a difference that could make it cheaper and easier for manufacturers to integrate high-speed optical data connections into tomorrow's computer chips. The startup Semerance was founded to implement the production process in functional on-chip photonic crystal membrane lasers. The team published its findings in Nature Photonics.
Before we go, we want to let you know that our webinar on photonics and bioimaging applications is available on demand on photonics.com.
Click the link in this video or visit photonics.com/webinars. If you're not already registered, it will just take a moment to do so.
Then you'll have access to the two informative presentations made by our speakers, Meng Sui and Lihong Wang.
Well, that's it for this edition of Light Matters, the industry's only weekly newscast. We'd like to hear from you. Tell us what you like or don't like about our program. We welcome your comments and suggestions at lightmatters@photonics.com.
You can join John Russell from Australia, who said he loves the show but wishes we'd slow down a little.
I'm working on it. Anyway, you'll find links to share and subscribe to Light Matters by clicking the Share with Friends button on our video player.
Thanks for watching, and we'll see you next week.
Hi, my name is Srinivas Narasimhan and I'm an associate professor at the Robotics Institute in Carnegie Mellon University, and I'm going to be describing a joint project that we are doing in collaboration with Intel. And this is a smart headlight that can allow you to see through rain and snow. So imagine you're driving at night and it's pouring pretty hard. You see all these rain streaks coming at you, the bright flickering streaks. And so a headlight essentially lights up all of these streaks in addition to the road, and it makes it very stressful to drive at night. So what we are doing is we are being a little bit smart about it, and we are going to figure out how to stream light in between the raindrops or snowflakes so that you don't see the weather in front of you. Okay, so it sounds like a very simple idea, but it's a very technically challenging engineering challenging problem, because we had to first detect where the raindrops are, where the snowflakes are, and very quickly predict where they're going to be in the next millisecond and turn off the light trace at that location. Okay, this gives you a feeling that you're not seeing anything in front of you. Okay, and that hopefully can make it less stressful to drive in rain and snow. Okay, so this is the setup that we have here, and that's Robert, my postdoc, who's working on this. He's the main guy making this possible. And so we have here behind a camera and a projection system that's acting as our smart headlight. So the camera is very quickly going to be imaging where the drops are, where the snowflakes are, and then it's going to pass it on to the computer, which is going to predict where the snowflakes are going to be or the raindrops are going to be in the next few milliseconds. And that's going to be passed on to a projector that then sends out light patterns that are binary, black or white. Black wherever we don't want to hit the raindrop, and white wherever there's no raindrop. Okay? So here's our very sophisticated raindrop generator. We have a bunch of valves here that are controlled, and water is fed through this tank. And when the valves open and shut, you have drops coming out. So now you see the drops are coming out. It's about 2 drops per second, and there are about 16 valves here. You can always do many more, but we just put in 16 for now. And so this is about 32 drops per second. So if you collect this over an hour, given the radius of the drops, it's about 90 millimeters per hour. So it's a very strong rainfall, but it's in a small region for now. Okay? So there's no restriction as to how much the field of view needs to be, but for this demo, we are just keeping it into a small field of view. And so if the if you have a standard headlight that is just lighting up all the way through, you see a lot of these bright flickering streaks. Okay? And now Robert here is going to turn on the smart headlight. Give a few seconds. Now you don't see the rain at all. Right? So what it's doing is it's trying to figure out where the drops are, and very quickly, before you even notice it, it's streaming light in between the rain and the snow. In this case, just the rain. Okay? So just as a comparison, Robert will now toggle. That's the standard headlight. Okay? That lights up all the time, and that makes it stressful to drive. We're showing a comparison between what happens if you light up the drops and what happens if you miss them. That means you're not seeing those drops as brightly as before. And so the idea is, if you make this system faster and faster, you can now put it on a car and travel at, let's say, 60 miles per hour in a thunderstorm and reduce the visibility of rain by about 70 to 80%. Okay? To get there, we need to be about 400 hertz, so we need to react at about 400 hertz. Right now the demonstration is going at 120 hertz. So we think this is feasible enough, and we will be able to move towards that 400 hertz within a few years. And then we can compactify this system, we can integrate the imaging, the illumination, and the processing within one device and put it in a car.